Bismillahir Rahmanir Rahim. Assalamu alaikum and welcome back. In this session, we are going to talk about two-level factorial designs. Up till now, we have discussed the basics of design of experiments, and we have only focused on a single factor design. And even before that, we have only focused on analysis and regression for a single factor. If you recall, we called it the simple linear regression, in which we were ascertaining the relationship between a dependent variable and a single independent variable. So that single independent variable in the context of design of experiments is called a single factor. However, in real life, most of the experimental setting that we are interested in have two or more factors, and these factors can often interact as well. So these are some of the challenges when we proceed and advance from the very basic single factor designs to multi-factor designs. To counter this and to keep things simple, we are going to focus only on multifactorial designs in which every factor has two levels. So these two levels can be defined as a low level and a high level. This is an arbitrary definition and it depends on the factors we are considering, but we can think of two levels of that factor, and we can call one level or one setting as the low setting and the other as high setting. The low setting may mean the absence of that factor, or it may mean some level of that factor. So when we consider factorial designs in which we have multiple factors, the important concern arises of interaction. And if you recall, we defined interaction as the fact that the effect of a factor depends on the levels of other factors. And if the levels of other factors change, the effect of this factor would change as well. To illustrate this, let's consider a simple example. So you can see on the slide now two simple cases. This is a two-factor, two-level factorial design. So because of that, when you have factors each having two levels, these factors in this case are known as factor A and factor B. Each one of them have two levels. So all in all, we would be having 4 experimental points. If you see, we can, in a two-factor factorial design, you would have 4 points, and they are represented as the low level of A with low level of B, the low level of A with high level of B, and similarly for the other cases. You would have a total of 4 experimental runs, which you can see on the slide now. So how do we determine the effect of a factor? It's quite simple actually. We take the average of effects when the factor is at a high level, and we subtract from that the effects when that factor is at the low level. So in the first case, in which we do not have interaction, you have 4 data points, and the response on those 4 experimental treatment combination points is shown. So in design of experiments, the design and analysis go hand in hand. First of all, we construct what experiments we are going to perform, what are the levels of the factors, and then using that design, we actually conduct the experiment. So the readings that you see on the slide now above every point is conducting of an experiment and noting the observation. So the effect for factor A is calculated as the average effect at the high level and subtracting from it the average effect at the low level. So this is 40 plus 52 divided by 2. So if you see, 40 is the case where factor A is at the high level, and 52 is the other point where factor A is at the high level. If you note the 2 points where factor A is at the low level, it is actually 30 and 20. So we take the average of this and we subtract it from 40 plus 52 divided by 2, and we get the average effect of 21. Similarly, we calculate for B. We take the differences of the average of B at the high level and the effect of B at the low level, and we get the effect value to be 11. Similarly, we can calculate the effect for A and B. A and B is the effect of the interaction of factor A and factor B. In this case, when we take the average of the response at the high level and subtract from it the response at the low level, we get a value of -1, which is negligible. So because of that, we can say that the interaction is negligible. So in the other case where you do have interaction, the interaction manifests itself as the crossover of lines that you can see on the bottom right graph. You see there is a crossover effect, and that is because the effect of AB now is quite significant. In fact, it has the highest effect. The effect of factor A is just 1, the effect of B is -9, and the effect of AB is quite significant. It is -29. It is precisely in this kind of a case in which one factor at a time design would fail, and we need to have multi-factor experiments. And the simplest kind of design which deals with multi-factor experiments is the design that we are going to focus on today. So if we see the outline of this lecture now, there are two parts of this lecture. The first one is the two-level factorial design without replications. So we represent this design as 2 raised to k. This is because in such a design we would need to have 2 raised to k experiments, and 2 here represents the number of levels of every factor, and all in all we have k factors. So for such a setting you need to perform 2 raised to k experiments. If we do not perform any replications, that is at each treatment combination, we do not perform multiple experiments, we have no idea about the experimental error. So to calculate that, we need to perform replications. And the second part of today's session would focus on two-level factorial design with replications. In such a design, you need to perform 2 raised to k into r experiments. And because of that, such a design is represented by the shorthand of 2 raised to k multiplied by r design. So we start with the first part of today's session, in which we are going to talk of two-level factorial design without replications, in which we have k factors, each having 2 levels. So one thing that we may ask ourselves is, why are we limiting ourselves to only 2 levels? Why not conduct experiments for multiple levels like we did for the one factor experiments? So the answer to this is that this is for pragmatic engineering reasons. In fact, such designs and the two-level fractional factorial designs that we would cover next in this course are some of the most common designs that are used in engineering practice. This is because in industry and in any practical setting, time and resources are very important, and you do not want to perform more experiments than is absolutely necessary. So in fact, you can get a very good idea, especially at the start of your study, because at the start of your study you have a lot of uncertainty, and at that time you can just do the experimentation for 2 levels of the factor. So while the factor may potentially have a lot of levels, you can choose 2 levels and then perform experimentation on it. Based on this, we can identify those factors that are important, and then subsequently we can focus on them and even incorporate more levels. So this is a very good approach in which we have a sequential approach to experimentation. We do not just get head on into doing a lot of experimentation in which most of the experiments are redundant and unnecessary. In fact, what we do is we first of all try to figure out what the most important factors are, and then we can hone in onto them and try to figure out the exact optimal level setting of those factors. So there is a catch here, however, and that catch is that such designs are most appropriate when the relationship between a predictor and a response is monotonic, which means you have a single direction in which the relationship is moving. Because if you do not have that, as you can see on the slide now, you have two graphs shown. In the first graph, the effect is unidirectional, and that is precisely the case in which two-level design is most appropriate. In the other case, the bottom right graph, you see that the effect is not unidirectional. Beyond a certain point, you have a knee of the graph, and beyond that, the response is actually going down. So there is no clear-cut way the effect is operating. It's not that if you keep on increasing this effect, you would have also increase in the other variable. Beyond a certain point, this relationship in the case of the second graph is reversing. So it is in the first case where two-level design is most appropriate. In the other case, based on the 2 points that you choose for your levels, you may even get misleading results. So the case in which such an approach would work would be typically like performance versus memory, performance versus the number of disk drives that you have on your system. You intuitively expect that if you keep on adding memory, the performance would keep on increasing and would keep on improving. So in this sense, we have a monotonic relationship, a unidirectional relationship. So this is one assumption that we must keep in mind, and we must take care to ensure that we apply two-level designs only where they are appropriate. Okay, let us begin two-level factorial design by the most simple case, and then we will build upon it and generalize that to more elaborate designs. The simplest design that we can think of in which we have two levels is that you have only two factors. Remember, we are interested in multi-factor experiments. So single factor is out. The next simplest thing is the two-factor design. So such a design is known as 2⁻² design. You have two levels, and because of that, the base is 2, and you have two number of factors, and because of that, the exponent is 2. Such a design is known as 2⁻² design. Let us consider an example of this to build intuition of how this design works. So you can see on the slide now an example in which you have two factors. The response variable that we are interested in is performance in millions of instructions per second, MIPS, and the factors that is going to influence the response is the cache size and the memory size. The cache size has two levels, 1K and 2K, and the memory size also has two levels, 4M bytes and 16M bytes. So in a 2⁻² factorial design, you will need to perform 4 experiments, and that is your design. You perform the experiments, you get the results, the values for these 4 experimental runs, and those observations are listed in the table on the slide now. So the idea is we want to build a model of this, and to do that we have an indicator variable which tells us where the factor A is. Is it at the high level or is it at the low level? Similarly for the other factor. So the convention is that we use -1 if a factor is at the low setting, and +1 if the factor is at a high setting. So here we see that x of A is equal to -1 if you have 4M bytes memory, +1 if you have 16M bytes memory. XB is -1 if you have 1 kilobyte cache, and it is 1 if you have 2 kilobytes cache. So this is the design. Now we are interested in building a model of this. And this is actually an extension of the simple linear regression that we've studied. In simple linear regression, we had a single independent variable. In the context of design of experiments, this is the factor. And you have a single response variable and you see the relationship. In the case that we are studying now, we have 2 factors. So this kind of a regression model is known as a multiple regression model. And that model is shown on the slide now. Its form is y is equal to q naught plus qa xa plus qb xb plus qab xa and xb. As mentioned earlier, xa and xb are just the indicator variables indicating where the current factor level setting is. It would be +1 for high setting and -1 for low setting. And the QIs are the effects coefficients. So Q0 is the mean value. QA is the effect of factor A. It is the effect coefficient of factor A. QB is the effect coefficient of factor B. QAB is the effect coefficient of the interaction between A and B. And we can list down the observations against different values of XA and XB. So for example, in the first equation that you see in the observation, XA is taken as -1, XB is taken as -1, and XA, XB is taken as +1. And because of that, we have one side of the equation as Q naught minus QA minus QB plus QAB, and this is equal to 15. I hope you get the idea. By changing XA and XB, you can put into a mathematical format our observations. So you have 4 equations here, and you have 4 unknown variables, Q naught, QA, QB, and QAB. So we can now solve for these variables, and the regression equation that we get is equal to y is equal to 40 plus 20 XA plus 10 XB plus 5 XA XB. Let us now try to understand the intuition of this regression equation. This basically tells us that the average mean value that you would have is 40. If the factor A is high or low, it is going to produce an effect of plus or minus 20. If it is at a higher level, you would have XA is equal to 1, and you would have an effect of plus 20. If you have A at a lower level, XA would be -1, and you would have an effect of minus 20. Similarly, for the other factors as well as the factor interaction. So the effects are shown here, and based on this, you have now divided the overall performance into simpler components that are contributed by the factors. This is very useful because it helps us understand what are the most important factors, and then you can put your money on that. For example, we are interested in knowing, we have all these factors, what is the most important factor which is contributing to performance? Based on such a multiple regression model, we can find out the contributions due to every factor, and based on that we can make some conclusions. So the computation of effects, as was shown in the previous slide, is now seen in a different context, and we see how do we actually go about calculating the effects in a simple manner, because we do not want to solve 4 equations every time. If there is a simple method, and a simpler method exists, so you can rewrite the equations and through some algebra produce equations that are shown on the right hand side of your slide. Now you have 4 equations in which you have a simple expression of what Q naught is, what QA is, what the effect of factor QB is, what the effect of interaction AB QAB is. So if you observe carefully, this is quite interesting, and this is something known as a contrast. If you observe, for every equation for Q0, QA, QB, QAB, the factor effect coefficients add up to 0. So in the case of QA, if you add the coefficients of y1, y2, y3 and y4, they sum up to 0. So that is the case for QA, that is the case for QB, and also the case for QAB. This is very useful, and we would see that this actually facilitates analysis a lot. So based on just these formulas, we can find a more convenient way of determining these effects, and that method is known as the sign table method, a very simple way of calculating the effects. So let us see how this thing then works. You have on the slide now the number of experiments that you're going to perform and the different settings of A and B, and for that you calculate the observational value. So at the lower setting of AB, you calculate the observation and you call that y1. Similarly, for a high setting of A, low setting of B, you calculate y2. Similarly, you calculate y3 and y4. One thing that you can observe is that Q of A is simply the column A multiplied by the column Y. So it would be minus y1 plus y2 minus y3 plus y4, and then we take an average of that. We divide it by 4. Similarly, QB is column B and multiplied by column Y. That gives us the coefficients of different y1, y2, y3 and y4. Alternatively, we can build a sign table, and the sign table is what we are going to use after now. This is a very simple method. You make two columns. The first column is the column A, which is the first factor. The second column is column B, which is the second factor. For the first factor, we list down an order of coefficients which is known as the standard order, or also the Yates order, in which in A we would write -1 plus 1, -1 plus 1. For B we would write -1 minus 1 plus 1 plus 1. If we had a third factor, we would have written -1 4 times and plus 1 another 4 times. If you had another factor, similarly you would keep on extending according to this binary logic. So I hope this thing is clear. After making these two columns, you would create another column A and B. This is the interaction between A and B, and you can simply calculate that by multiplying the coefficient of A and the coefficient of B. In the first row, both of these are -1, and so you can calculate AB. So you simply need to list down the binary logic order that we defined for the main factors, and the interaction can simply be calculated by multiplying the appropriate columns. So after having done this, we produce another column which is the first column, and in that we list all ones. And in the last column, which is on the rightmost side, we list the observations. So now from here we can very simply calculate the effects, and that is the first column is multiplied by Y. So you would have 1 into 15 plus 1 into 45 plus 1 into 25 plus 1 into 75, which gives us 160. This is the mean value. If you see, this is adding up all the responses, and then we divide the total that we have created by the number of rows we have, and the number of rows are 4. So we divide 160 by 4 to produce the mean effect, which is 40, consistent with what we've discovered just a little ago using a more elaborate method of solving 4 linear equations. For A, we follow a similar protocol. We multiply the coefficients with the y column and then we take the sum of it. So this would be minus 15 plus 45 minus 25 plus 75. This gives us a sum of 80, and then we take an average of it by dividing it by 4, and the effect of A then comes out to be 20. The effect of B comes out to be 10. The effect of the interaction comes out to be 5. And from this we can calculate the regression model. I hope you can connect the dots. So if we were to use this to calculate the regression model, that would be y is equal to 40 plus 20xa plus 10xb plus 5xa xb, and that would be your regression model. So let us move forward now and discuss another method of determining how important a factor is. And this is the way in which we allocate and find out how much of the variation is explained by individual factors. This should sound familiar to you because we did this for one factor experiments as well. So we are now going to extend that concept and use it for the 2 raised to k designs that we are currently studying. If you recall, we mentioned that variation is a little different from variance. Sample variance is defined as shown on the slide now, and you would observe that there is also a denominator term in which there is the number of degrees of freedom that you have. Variation, on the other hand, only takes up the numerator of this sample variance, and we call this variance as the total sum of squares. So we represent this as SST, and for a 2 raised to 2 design, SST is equal to 4qa square plus 4qb square plus 4qab square. The derivation of this can be seen in your textbook, but for now we are going to take this on faith that SST is equal to this, and the individual terms are known as SSA, SSB and SSAB respectively. So let me reiterate, SSA would be 4qa square, SSB would be 4qb square, SSAB would be 4qab square. This is the case for 2 raised to 2 design. So now if we are interested in explaining away the variation by explaining how much of the variation is explained by factor A, how much of the variation is explained by factor B, and similarly for the interaction AB, we can simply divide SSA by SST, SSB by SST, and so on. So if we do that, we calculate the fraction explained by these factors and the interaction AB. So we can calculate the fraction explained by A, and we do that, and this comes out to be the factor A in this case of the example that we are studying of memory and the cache system. The factor A is memory and factor B is the cache. So we are going to now calculate and apply the formula of SST and how we are going to allocate the variation. We see that the grand mean or the overall mean of the response comes out to be 40, and the total variation or SST as we have defined it, when we calculate that, we are getting a value of 2100, and this is in turn composed of SSA, SSB and SSAB, the variations explained by A, B and AB respectively. So again, when we calculate via that method, we also get a value of 2100, which explains that both these things are equal, SST and the sum of SSA, SSB and SSAB. So when we calculate the amount of variation explained by memory, this comes out to be 76%. And when we calculate the variation explained by the cache, this comes out to be 19%, and the interaction between these two factors is 5%. So from our analysis, it appears that memory is the most important factor. And if we have to, for example, put money on just one factor, it has to be memory. And that's the whole exercise of this analysis, trying to find out what are the most important factors. So up till now, we have focused and developed the idea of factorial designs for two factors, each having two levels. So this was the 2 raised to 2 design. Let us now move forward and talk about the general 2 raised to k factorial design, in which k is not limited to be only 2. It can be more than 2. So when that is the case, let's say k is equal to 3. So 2 raised to 3 design, I hope you can explain how many factors we have and how many levels each factor has. If it is 2 raised to 3, you have 2 levels and 3 factors. So in a 2 raised to 3 design, we need to conduct 2 raised to 3 experiments, which is 8 experiments. And on the basis of that, we can estimate 2 raised to k effects as well. The main effects due to the main factors, 2 raised to 3 has 3 main factors. So the k in 2 raised to k represents the main factor. And you would also have some two-way interactions. And you would also have a 3-way interaction because you have 3 factors. And the way to calculate is given on the slide now. So one thing that you can observe here is that the main effects are quite a lot less than the number of total experiments that you need to perform. They're also a lot less than the number of total effects that you are estimating. You can see here that you can estimate 2 raised to k effects, and if you only have k main factors, you would have some 2-way interaction and 3-way interaction. In practice, what is observed is that it is very rare to have interactions of the order of 3. For example, it's very rare to be having 3 factors that have interacting effect. It is somewhat common to see 2-way interactions, but we can ignore 3-way interactions because for all practical purposes, they happen very rarely. They do happen, but in a study conducted by a professor at MIT and reported by Douglas Montgomery, the author of Design Analysis of Experiments, it happens less than 5% of the times. So we can ignore 3-way interactions. So when you have more and more number of factors, you would observe that you actually do not need to cater for these high-level interactions. You can ignore 3-way interactions and more than that, 4-way interaction, 5-way interaction. If you have more number of factors, you can focus on the main effects and the 2-way interactions. And typically that is what we focus on. So let us now study a design example of 2 raised to 3 design. So we have a case study here in which you have 3 factors, because this is a 2 raised to 3 design. The 3 factors, factor A, B, and C, are the memory size, the cache size, and the number of processors respectively. And each of these factors have 2 levels. You can see all the details on the slide now. The model that we are going to use is also shown on the slide. This is again a multiple regression model in which you have more than one independent variable. In fact, you have a lot of independent variables, the main effects, as well as the 2-way and 3-way interactions. So how do we analyze this? We've developed the whole idea of 2 raised to 2 designs to initiate this intuition in you so that you can extend this to more elaborate designs. So the sign table method that we used can also be used here. So we take that approach. We list down the main effects A, B, and C, and we use the same way of generating the columns. For the column A, you would have -1, +1, -1, +1, and so on. For B, you would have -1, -1, +1, +1, and so on. For C, you would have 4 minus 1s and you would have 4 plus 1s. All in all, you would see that every column is having 4 minus 1s and it is having 4 plus 1s. I'm talking of all the effects. For the first column, you have all 1s. And then using the same method that we use for 2 raised to 2 design in the example that we did for that, we can calculate that the mean comes out to be 40, the mean effect. And the effect due to A can be calculated to be 10. The effect due to B can be calculated to be 5. And so on, we can estimate the effect of all the main factors of the two-way interactions and also the three-way interaction. So you can see that the two-way interactions are not significant here. The three-way interaction is also not significant. So what is significant then? We see that most significant factor is the factor C, and then you have factor A. So you can actually use the method of allocation of variation to see which one is the most important factor. So for that, we calculate SST, the total sum of squares, and we then allocate proportions of this to individual factors, the two-way interaction and the three-way interaction. Doing that, we see that number of processors, the factor C explains 71% of the variation, and because of that, we can conclude safely that this is the most important factor. We can now talk about two-level factorial designs in which you also have replications. These replications are very important for estimating the experimental errors and for calculating things like the confidence interval, and the experimental error can also be quantified. So let us now study the cases in which you have R number of replications, you have 2 levels, and you have K number of factors. Such designs are called 2 raised to K into R designs, because the number of experiments that we need to perform is 2 raised to K into R. You have R number of experiments for each one of the 2 raised to K combinations. So let us see for this design how to compute the effects. You can see on the slide now that you are shown a table in which again you have 2 levels and you have 2 factors, and for every one of the combination setting you're also taking 3 replications. So that is the 3 numbers within parenthesis under the Y column. So this is the usual sign table that we created for 2 raised to 2 design. So you have 2 main factors, you have a two-way interaction, and the way of calculating the sign table is exactly the same, but under Y column we have now 3 readings, and because of that now we need to calculate the mean of this, and because we have multiple readings we can also estimate the error or the amount of random variation in our observations. So how do we compute the effects? The model is shown on the slide. So the only difference from the model that we earlier studied is the additional E term that you can see at the end of the equation. So instead of using the Y column in which we have 3 readings, we are going to use the mean Y bar column, and exactly in the way we calculated and analyze the 2 raised to 2 design, we calculate the effects and we see that Q naught is equal to 41, QA or the effect due to factor A is 21.5, the effect due to B is 9.5, and the interaction term is 5. So the difference comes into the picture when we now analyze E in more detail, and for that we can estimate the response Y of I. This is the estimated response, and you see that in this there is no E term. We're trying to catch the experimental error, and the experimental error is the difference with our actual observation via the predicted response, which we predicted through a model, which is shown on the top of the slide, the one in which we have y subscript I with the hat on top. So this is best explained through an example, but before that, after having explained E of ij, if we take summation of Eij over all j's and all i's, in which I is from 1 to 4 and j is from 1 to r, we get the sum of squared errors. And from this we can explain how much of the observed variation can be explained as due to random variation. This is important because, as discussed earlier, whenever we want to statistically analyze experiments, we need to get a grip on what the actual amount of error is, and this helps us do good statistical analysis. So this whole idea of 2k raised to r design is best explained through an example, and we are going to continue on this example, and we see that the estimated response according to the multiple regression model that we formed, the estimated response yi with a hat on top, this is 15, 48, 24 and 77, and we compare it with the measured responses, and from that we calculate the different values of E. From here we can calculate SST, and that is in turn composed of SSA, SSB, SSAB and SSE. All of it is the same as 2 raised to 2 design, except that we have an additional SSE term. In the earlier design, in which we were not having any replications, you would notice now that there was no SSE term. We did not have an estimate of the amount of random variation, but now we have. So this is a bit of a trade-off. To find SSE, you need to do replications. So how do we explain the total effect in terms of the effect due to factor A, B, AB? So this is now shown. We see that SSY is calculated as 15 square plus 18 square plus 12 square plus 45 square, and we keep on adding this till we get the whole answer, the whole SSY. This is equal to 27,204, and we also calculate SS naught, SSA, SSB, SSAB, SSE. SST is actually the difference between SSY and SS0, and you can check the calculation by following the terms written on the slide. So after that, we can now turn to allocation of variation. How much of the variation is explained by different factors? So we see that factor A explains SSA over SST amount of the total variation, and this comes out to be 78.88%. This appears to be the most significant factor. Factor B in turn explains SSB over SST of the total variation. So this is 15.4%. Interaction AB is just 4.27%, so it's not really significant. And the key to 2 raised to KR design, the amount which is unexplained is now shown, and it can be calculated as SSE divided by SST. And we calculate that and we find a value of 1.45%. So this tells us that the amount of error is relatively low, and because of that we can have a lot of confidence in our conclusions that factor A is perhaps the most important factor in this setting. We can now conclude this lecture and talk about the most salient points of 2-level factorial design. The importance of having only 2 levels is that we want to reduce the number of experiments that we need to perform. In 2 raised to k experiments, the pro of such an approach is that we can estimate all the main effects and also all of the interactions. And we can do this by reducing the number of experiments by limiting the levels per factor to only 2. So this is quite useful at the start of an engineering study, and experimental design is often done in an iterative way, in which first of all you have a pre-screening phase in which you decide on initially the most important factors. And this actually follows more or less the Pareto principle, that not all of the factors and not all of the interactions are important. And in fact, you need to find out the vital few factors and the vital few interactions from the trivial many. And then after having determined that what are the most important factors, what are the most important interactions, you can then do a more thorough subsequent study to find out particular levels. You can have a more extensive design to optimize on your process. The downside of a 2-level full factorial design is that even with just having 2 levels per factor, if the number of factors are enough, you would need to perform a lot of experiments. As an example, if you only have if you have 10 factors, you will need to perform 2 raised to 10 experiments. So this is the case when you only have 2 levels, but because there are so many factors, you would need to perform of the order of 1000 experiments, which cannot be performed in practical settings. So another concept that we would develop in a future session is to only run some of the experiments of the full factorial, and that is what we call the fractional factorial design, in which we either run, let's say, half of the experiments or 1/4 of the experiments or 1/8, 1/16, and so on, because in most practical settings it is enough for us to only estimate the main effects and some of the second order interactions, because it is quite rare to find interactions of 3 order, and beyond that the chances of that happening is quite negligible. Because of that, we can actually learn a lot by doing just a fraction of all the experiments of a full factorial design. A full factorial design is most relevant when you have limited number of factors, and in most practical settings it is advisable that we limit ourselves to a limited number of factors. You should try to have in your experimental settings factors of not more than 5, because when you get to more factors than that, then the chances of problems occurring and the chances of having too many experiments increase. So a good way to understand where to apply 2-level full factorial design is to limit it to the cases where you have either 2, 3, 4, or 5 factors. Even 5 factor is a little on the higher side, because it requires 2 raised to 5, 32 experiments. Beyond that, in most practical settings, we only use a fraction of all those experimental runs, because in the case of, let's say, 6 factors, we do not expect 63 effects to be significant. We only expect a few of the effects to be significant according to the Pareto principle, in which there is only a few significant effects and all the other effects are typically having negligible contributions. So we will continue next time. When we talk about fractional factorial design, we will still be talking only about 2-level designs, but then we will be choosing a fraction of all the entire experimental runs that we need to conduct for the 2 raised to k experiments, and while only keeping a fraction of all those experiments, we will choose such a fraction which will help us determine the main effects and the most important interactions in a similar amount of precision. So till next time, Assalamu alaikum wa rahmatullah.